Okay, question 5. Prove this identity. We end up having 2 cos squared 45 degrees minus x is equal to sine x plus cos x squared. This side I am more comfortable with. This side ends up irritating me a little. I've got a special angle over here. I've got a 2. I've got a cos squared. I've got squares on both sides. So they're a little bit frustrating, but when I've got a square on both sides, what I want to do is I want to square root both sides. If I square root this side and I square root that side, my identity ends up simplifying down to the square root of 2 still stays the root of 2. And then we end up having cos 45 minus x. And on the right hand side, we have sine x plus cos x. Now I want to change this into a sine x plus cos x. And the only way I know how to do it is by dealing with this compound angle on the left hand side. Sorry, that should have been a big equal, and this should be now left hand side. So we keep our root 2 out in the front, and we change this cos 45 minus x into its compound angle. So we end up going cos 45 degrees times cos x. The minus becomes a plus, and you have sine 45 degrees times sine x. Remember, cos compound keeps all the coses to the one side. And I know my special angles. If you don't know your special angles, always have them drawn on your Cartesian plane just before you start any activity. We're going to deal with the angle 45, but we also know 30 degree and 60 degree is a special angle. So we've got 45, 60. And the way that I remember it, always the same way, it's counting down. 4, 3, 2, 1, 0. This is 2 units long. Therefore, this length will always be 2, and the square of 2 is 4. So the square root of 4 is 2. The square root of 3, the square root of 2, the square root of 1 is 1, and the square root of 0 is always 0. We start on this side again. This is 2 units in length. So this is the square root of 4, which is 2, the square root of 3, the square root of 2, that's a 2, not a 3, and the root of 1. You end up getting your coordinates. Easy enough. 4, 3, 2, 1, and 0. So we're looking at 45 degrees, which is this whole angle over here, and this ends up being my x value and my y value, and this 2 units is my r value. Okay, so cos 45, well, we know cos 45 is x over r, and we know sine is y over r. We'll know that forever, right? Because you all learned it in grade 8. So when we go here, we keep root 2 out in the front, and we end up having root 2 over 2 times cos x plus root 2 over 2 times sine x. And when we distribute this root 2 in, root 2 times a root 2 ends up giving you 2 over 2 times cos x. And times that root 2 in, we get 2 over 2 sine x. And 2 over 2 is 1, so that simplifies down to cos x plus sine x. This is a nice hint towards your assignment that we end up doing for trig in term 1. Okay, you'll end up having your root 2 out at the side there. So, I hope that made sense. I hope that you identified you had a square on both sides. Don't forget that this root 2, and if you remembered your 45 degree angle, you would have known that the root 2's would have times together. So you do need to think ahead before you actually even start writing, because it really does help, but it means that you need to know your work really well. And the only way you're going to know your work really well is if you practice. Okay, so now we end up having, let's just change my color pen. Now we end up having Question C, sine 2x plus cos x over cos 2x minus sine x minus x is equal to minus 1 over tan x. I know we always want to simplify the tans, guys, but in this case we've got double angles over here. So let's simplify the left-hand side to see if we can actually get it to a negative 1 over tan x. Okay. Now, whenever we're trying to simplify, we need to think about ways in which we can factorize. If I've been given a sine 2x, there's only one ratio that we can use, and that ends up being, so let's take the left-hand side, that ends up being 2 sine x times cos x plus cos x. In the top here, I can take out a common factor of cos x, and I can simplify that down, which we'll do in the next line, but let's deal with the bottom. At the bottom, we've got a cos 2x minus sine x minus 1. That's nice enough, guys. We know that this needs to be factorized. The only way I can factorize it simply is by making a cos 2x into a sine x. Can I do that? Here I've got a cos 2a, I've got cos squared a minus sine squared a. That could possibly work, but I don't want to deal with the cos again. I want a purely sine item. So we can rearrange that. And this cos 2, and I'm just going to write it in its color, it ends up becoming 1. This whole guy over here becomes 1 minus 2 sine squared, and we're dealing with x's in this instance. Okay, now let's go back. We end up having minus sine x and minus 1. Now, simplify the top or take out a common factor. The top's common factor is cos. Let's take cos x out, and we're left with 2 sine x plus 1. That's going to give me a hint at what one of my brackets at the bottom is going to be. So let's go see what the bottom bracket ends up being. I've got a 1 minus a 1. 1 minus 1 leaves me with nothing. Then I've got a minus 2 sine squared x minus sine x. Both of them have signs in it. And you see there's a negative in both of them. I'm going to take a negative sine x out of that bracket, and I'm left with 2 sine x. Take a minus sine x out, I'm left with a plus 1, which means I have a top ratio, a top identity or a top term and a bottom term that can be cancelled out, and I'm left with cos x over minus sine x. Now this cos x over minus sine x, I know that my tan ratio is sine over cos. So if I had to flip this, then I would be able to get tan x, but I can't flip it. But what I do need to understand that if I flip this, surely I should be able to flip that. So let's look here. I'm going to do scribble writing over here in the color that it needs to be in. If I have sine theta over cos theta, and it is equal to tan theta, I know that tan theta is over 1. And if I had to flip this being cos theta over sine theta, I can flip this 1 over tan theta. And do I not have cos over sine? I definitely do. So because I've got cos over sine, I can end up going 1 over tan theta. Problem is I have a minus. I can put that minus anywhere, guys. I can put it over there. I can put it in front of it over here. And I can put it with the 1. It actually doesn't matter. It all means the same thing. But in this case, we're just going to put it at the 1 just so that it looks like the right-hand side. So I've proven my left-hand side is equal to my right-hand side. And it's the first real double identity that we've actually used so far.